Welcome back to the next additions to complex number discussion. All right, now previously we have looked at the how do we represent complex number in the rectangular form or Cartesian form, and then we can also represent complex number in modulus argument form. And then today we're going to look at how do we represent complex number in its exponential form, or sometimes is known as the Euler format. Right? Now, before we start with the exponential form, let's walk through a bit of theory behind how this complex number uh, was able to be represented using Euler form in this case. Right? Now, the first informations that we need to know of would be here. Now, the trigonometry ratio of cosine, or sine in this case, now is given by this series here. Now, this series was obtained from, you can say that from Taylor-Maclaurin's expansion. Right? So, if you are interested to look at how this series is being produced, you can read up Taylor-Maclaurin's series expansion. Right? Okay, so here I will skip the explanation as to how this Taylor-Maclaurin works. I will include that in the extra video. There, right? Now the second representations of sine in the form of Taylor-Maclaurin series would look something like this. Okay, and then lastly, we will need to use the definitions for exponential, which is given by this. E raised to the power of x, or theta here is given by this series here. I think I forgot to include one section here. Just let me include that. Because this is an infinite series, so therefore it should be add on until infinity. So these are the main definitions that we're going to use to derive the Euler format that we can use to represent complex number here, right? Okay, now before we continue, I'm going to bring this back here one more time. Okay, so I'm going to put it down here so that it's easier for us to see. Okay, all right. Okay, let's look at this here. Now, once this is in this form, just to recap, we have cosine can be represented in this series, sine can be represented in another series, whereby the exponential can be represented in this series itself. Right? So by using all this, we get to derive the Euler form for complex number. Now let's try this out. Now, for any complex number in the Euler form, so Euler form can be written as such. Okay. Can be written as I theta. So I theta is the same by using this series here. We can write down as 1 plus I theta plus I theta square and then you have this. And so on and so forth. Right? Now that will be our series, and then we try to simplify this algebra. We will get 1 plus I theta, and then this one, just to recap, I square is an imaginary number that represents -1 here. And then we also need to know that I to the power of 4 is actually a 1. All right. So for that, I will get a theta square over 2 factorial, and then this one will be I theta cube over 3 factorial here, and so on and so forth. Right? And then by grouping all the real component and the imaginary component, we will be able to obtain this. I'll try to include 3 terms here just for comparison. And then I'm going to group those imaginary components together. Now that will be this. I think it should be minus. So just let me get that on. It's subtraction. I think this one is also subtraction there. Just let me correct that. It should be subtraction. Okay. Right, now there you go. That is our series that represent this exponential I theta there. And then from this Taylor-Maclaurin series of cosine and sine, we can represent this entire series in the form of cosine. You can see that it represents the same expansion. So this one we can write as cosine theta plus, and then this imaginary component can be represented as sine. So therefore, right, now you can see that this exponential I theta can be represented in the form of modulus argument form. And then we know that this is actually a complex number in its modulus argument form. Therefore, we can conclude that any complex number can be represented in this form. Okay, ei theta equal to cosine theta plus I sine theta. Okay, in this case, we make assumptions that the magnitude is actually 1 unit here, right? Okay, that's it. For the general form of any complex number, we prefer to write as this. So for any general complex number, we tend to write as r e I theta, whereby there is a certain magnitude for that complex number there. And then in this case, it's the same as r cos theta plus I sine theta. Right? Now, there you have it. That's the theory behind how this complex number can be written in from the Cartesian form, and then can also be written in the modulus argument form. And then lastly, how do we relate this modulus argument form in the form of Euler format that is given as exponential I theta there. Right? Now, from this point onward, we are going to make use of this result to ease our solving of any complex numbers in our following section. Right? So I hope that's clear. We're going to move on to the next section. Please stay tuned. Right? Let's try to apply that Euler form of complex number, which is given as, in this case, z equal to r exponential I theta. Right? Now, our first example. Now, assume that we are given the Cartesian form -1, whereby it is a general complex number with only a real component, -1. Now, for these types of complex number, it's always best to visualize that. Now, take for instance, try to visualize it very briefly. So we have a real section here. We have an imaginary section. Right. And then this -1 simply means 1 unit to the left. And then that will be our complex number. Now, first of all, in order to obtain its modulus argument form, we will have to figure out its argument, of course, measured from the real axis. In this case, it's counterclockwise. Now, therefore, the argument must be equal to pi here. Right? Okay, so I hope that is clear. And then the next property of this complex number will be its magnitude, like what's the length of this complex number with respect to the origin here. It's very obvious it's 1 unit here. So therefore, we can write down its modulus argument form in such a format. We will write this as z equal to the r is 1 unit, and then the angle is this. So I'm going to write down this format instead. So you can actually write it in this format, or sometimes you can simplify as just this, or you can write in this form, which is 1 cosine pi plus I sine pi. So it doesn't matter which format they are using, all these represent the same modulus argument form. And then for its exponential form, we can rewrite this as r is 1 unit, then therefore this one must be exponential I theta, because the theta is a pi, therefore we can write in this form. Now there you have it. That's how we write complex number from the Cartesian form into its modulus argument form, and then lastly we are able to represent complex number in the exponential form also. Now of course some of you are wondering, why do we need to have so many representation of this complex number? Now each one of these representation have its own pro and cons depending on the context of the problem that you are facing, right? Okay, so I hope the first question is clear there. All right. Okay, now let's move on to the second one. All right, second example. Let's look at second example. Given here, we have the Cartesian form of this complex number as 2 minus 3i. How do we represent that in the form of modulus argument format, and then its exponential counterpart here? Now, as usual, as I mentioned before, it's always best to draw the Cartesian form that represent this complex number, or in this case, we are using Argand diagram. Yeah. Please forgive me, I'm not using the correct term here. So it should be called Argand diagram because the x-axis represent real component, and then the y-axis represent imaginary. But from its fundamental structure, is actually a two-dimensional plane. Right? So this is 2 units to the right, and then 3 units down here. So I will roughly sketch this as something here. So this will be my complex number measured from the origin. We know that that is 2 units to the right, and then 3 units down here. Right? And then the argument will be measured from the real axis. In this case, it will be clockwise. And then do remind yourself, whenever you handle clockwise argument, it must be negative here. Right? Okay, let's look at what we have. First of all, we're going to work out the magnitude. So the magnitude for this complex number would be 2 square plus 3 square, of course. Don't forget to square root that. That will be surd 13. 9 with 4 is a surd 13. Unit from the origin itself, right? And then the argument. So the argument in this case, we can apply the inverse tangent or arctangent here, which is 3 over 2. Okay, so let me see what do I have there. It's an arctangent, so 3 over 2. Let me see whether I can get that correct. That will be an arctangent. Let me see what we have here. Okay, please forgive me. Give me a while. My calculator does not work properly here. Right, now let me try that one more time. That will be an arctangent 1.5 there. Okay. What do I have here? No answer at all. Something wrong with my calculator. Let me try one more time. 1.5. Okay, so that would actually give me 56 degree there, right? 56 degree. Or if you like to represent it in the form of a radian, that will also be accepted. So in this case, I'll just write it down in the form of a degree. That is approximately 56.3 degree there. And then once you have obtained the argument, don't forget this argument, because it's clockwise, in the clockwise direction, so it should be a negative here. Therefore, we are ready to represent this modulus argument form for this complex number. We will write that down as the R will be cert 13, and then we can write as negative 56.3 degree here, or we can write down as cert 13 cosine negative 56.3 plus I sine negative 56.3 here. Now, of course, if you are not a very negative person here, you might like to convert that to its simplified form. So cosine negative is always cosine in this case, because it falls in the fourth quadrant. There's just a simplified view of that. And then for sine, it should be negative. Okay, and then there you go. That is the modulus argument form. You can either leave it in this format or in its trigonometry form, which is also known as modulus argument form here. Right? And then lastly, the exponential form. So we can also represent this in its Euler format. That will be cert 13 exponential I. In this case, it's negative, so we will use a negative 56.3 degree. Okay, or you can write as cert 13 exponential negative I 56.3 degree, or you can use radian format if you prefer. Alright, I hope that is clear. We can look at a few more examples before we move on to the next section. Let's move on to the next example. Let's look at what we have here. Alright, now in this case, if we are given the modulus argument form, how do we represent that in its Cartesian form or in its exponential form? Right, now that will be much more easier in this case, I would say. Right. So for this, if you want to represent it in its exponential form, it will be very direct. So you can basically just write this as cert 2 is still a cert 2. Now the only difference is you have to turn it into exponential. That will be I pi over 10. And then we are done. So that is its exponential form. Now if you like to represent this in its Cartesian form, now that should not be a problem. It's exactly the same as this. Just let me write down here. That's a cert 2 cosine. That would be 18 degree. Just convert that to degree. It's easier for me to calculate in this case. So I sine 18 degree here. Okay. Now, of course, you can use your calculator in this case, and then just let me try in this case. So we have a cosine 18. Okay, what do I have here? 0.995, and then multiplied by 1.41. Okay, multiplied by square root of 2 here. So that would actually give me what I have is 1.34. So this is 1.34, and then plus the other one. Okay, just let me try to tabulate the other one. So sine 18, and then by a cert 2 also. Right, now that will give me an I 0.437, 0.437 here. Or if you like, you can write as 1.34 plus 0.44 I, if you want to standardize the decimal place. And then there you have it, how we represent complex number in this three most popular format: the rectangular form, the modulus argument form, and in its Euler form or exponential. Right? Now next I'm going to move on with another two more example. Next example. Let's see what we have. Now in this case we are given the Euler form of this complex number. How do we represent that in its modulus argument form? That should not be a problem. You can actually write this here. We can actually write this as cert2. You can just represent it as this 3 pi over 4, and then there you have it. Or if you like, you can represent that in the trigonometry form, which is cert2 cosine 3 pi over 4 Alright, now there you have it. That is the modulus argument form that you want to convert into in this case. Right? So you can leave it as it is. And then lastly, if you want to obtain its Cartesian form, all you need to do is just tabulate this using your calculator, for instance. But anyway, in this case, it's quite direct. I would say that this is the same as now that is the same as what we have here. That's the same as this is a negative, so there's a negative cosine pi over 4, and then this one is the same as pi sine pi over 4, and then that would actually give me this is 1 over cert2, and then plus 1 over cert2 also. And then basically we get a very nice answer in this case, knowing that this is 1 plus an I there. And then there you have it. How do we represent complex number from its Euler form into modulus argument form, and then lastly into its rectangular form or Cartesian form in this case. Right? I hope that has been useful. Let's move on to the last example. Let's look at this. If you are given another example on exponential form, in this case, all you need to do is just represent this in its correct notations. For instance, we can represent it in its modulus form. So for this, we can write that z is actually equal to 2 cosine 23 pi over 5 plus I sine 23 pi over 5 here. Yeah. Now the only difference now is most of the time our argument is set within this domain here, which is negative pi to pi, or it could be negative pi over 2 to pi over 2 in this case. But the argument that we have here has already exceeded this domain here, right? So therefore we have to readjust a bit here. Okay, now we can actually do it slowly here. We found that this is basically cosine. If you divide that, that is actually a 4 pi plus a 3 pi over 5 plus I sine, the same thing here, 4 pi plus 3 pi over 5 here. Now that is the intermediate modulus argument form. And then from here, we will try our best to simplify this. We know that the 4 pi basically means we go through a 4 cycle in this case, and then come back to this one here. So we can safely write this as 3 pi over 5 plus I sine 3 pi over 5 there. And then that will be the correct modulus argument form that satisfies this domain here, right? So I hope that is clear. And then lastly, in order for us to represent that in its Cartesian form, all we need to do is just tabulate this correctly. So in this case, we will get, what do we have here? We have 35. This is, okay, just let me try to do over 5. Right, now this one, if you press your calculator, I think it's better for me to use the calculator in case I make any mistake here. Alright, so just give me a moment, just let me check what we have here. By 5 here. Okay, so that will be 108. So let me see. Oops, 108. Yeah, okay. So cos 108. Okay, just let me try one more time and then check whether that makes sense or not. All right, so cos 108, and then that's what we have. 2 here. I get myself a negative 0.618, and then after that I need to tabulate this one here plus. Okay, just let me give it a try here. Sine 108, and then by a 2 here. So that would actually give me 1.90i, and then there you have it. That is the Cartesian form for this complex number. Now I hope that is clear at this point. Now, if you found that there's any error in any parts of this calculation or analysis, do drop a comment. Right? Thank you very much on that. We're going to move on to the next sections now. Number 2, how do we extend the ability of this Euler form that we can use to represent complex number? Right? Now let's try to attempt this question here. Using the Euler format of exponential I theta equal to cosine theta plus I sine theta here, we are about to show that cos theta can be represented in that form there. There's a reason behind as to why we want to represent that in that form. Is because if you guys have learned about hyperbolic functions, then you might be interested to make a connections between the hyperbolic functions and its trigonometry counterpart. So there is a relationship between the trigonometry ratio and the hyperbolic functions here, right? But for these discussions, we are not going to touch on hyperbolic functions. Right. Now, if you're interested, you can find that in the another video that I will upload. Right. Okay, let's look at this. How do we make use of this to prove that this is actually true? Right. Now, the first step, it would be very easy. All we need to do is now the easiest way is to prove it from the right hand side. So I will start from the right hand side expression. That is actually equal to this, equivalence to this actually. And then all we need to do is just make that correct substitutions. That will be cosine theta plus I sine theta here. That's the first part from here. And then the second part, I'll make a remark here. So E negative theta is the same as I negative theta here, which is the same as cosine negative theta plus I sine negative theta here. Right. And then this indirectly, based on the properties of cosine and sine, we can write it down like this, minus I sine, because sine negative is always negative in this case for this domain. So that will be add up with these sections here, which is cosine theta minus I sine theta here. And then from here, we can simplify that as it's very obvious here. We have 2 cosine theta, and then finally we will end up with cosine theta. Right. And then yes, we have indirectly, or we have successfully proven that. Therefore, we can conclude that yes, cosine is actually given by this one here. And then voila, well done on that. Right? Okay. Now that's the simplest proof that we can work with in this case. Of course, there is another way how we can actually prove this. Right? Now that one if you are interested to find out, you can give it a try by proving it from the left hand side, right? We'll do it on another separate video. If you have a comment, if you have methods, do drop your comment. Yeah, credit will be given to you, right? Okay. Now, next we're going to move on to the next example or the next section. Explore the properties in both multiplications and divisions of a complex number, right? Now, let's assume that we are given two complex number labeled as Z1 as such, and then we have another complex number that is labeled as Z2 given as such, right? So each one of them have their own argument. Let's make assumptions that their arguments are not the same, their magnitude may be different in this case, or they could be the same, doesn't matter here. Now we're going to look at how to work with the multiplications first. So for multiplication, multiplications between Z1 and Z2, the complex number number 1 and number 2 here. We can write that as this multiplied with this, which is indirectly this multiplied with this. But you can see that trigonometry multiplication is very lengthy. So it's always best for us to represent this in its Euler form. So Euler form state that we can write this case that represent the first complex number, and then we're going to multiply that with the second Euler form here, which can be written as R2EI theta 2 here. So there will be R2 EI theta 2. Now you can see how easy it is to manipulate this using index rule rather than using trigonometry. But by all means, if you're interested to work with trigonometry methods, you can always go ahead and do this. Right. Now in this case, we will get R1, R2. Of course, the magnitude can be separately multiplied. And then the E, because it's a common base, we can write this down as and then finally, if you want to convert back to its modulus argument form, that will be quite easy to accomplish here, which is exactly the same as this. And then there you go. How do we make use of the Euler form and then its modulus argument form to represent the multiplications operations for complex number? Right. So in the future, I will always advise you to use Euler if you are more comfortable with that. Its algebraic manipulation is more flexible compared to trigonometry. But then again, for those fan of trigonometry, okay, it's your choice. You can go ahead and give it a try. You will also end up with the same result here. Now, secondly, we're going to explore division. So divisions between these two complex numbers here, I make it short, just write down as Z1 over Z2, or if you are interested to study Z2 divided by Z1, also can. Both of them yield more or less the same result here. Now Z1, as I mentioned before, is best to represent it in its Euler form. Same go for Z2. And then in this case, we can write down R1 divided by R2 using index rule. We can write that as such. And then therefore, you can convert back to its modulus argument form, which can be stated as such. And then there you have it. That's how we apply Euler form to perform multiplication and divisions in a much more easier environment, I would say. Right? I hope that is clear. We're going to move on to the next section shortly. To look at one example here, example number 3, on how to apply that multiplication and divisions properties using Euler's form here. Let's look at this. If you are interested to work with the multiplications between these two complex number, it's always best to represent this in its Euler form. Personally, that's how I feel. But if you like your trigonometry, by all means, you can go ahead with that. Now, first of all, my strategy would be to collect all the magnitude together. So I'll take 4 with 3. That will give me a 12. And then, oh yeah, by the way, just let me rewrite this in the Euler form first before I do that. It will be much more clearer. So that will be I phi pi over 12 multiplied by 4 pi over 12 here. Now, once it is in Euler form, then you can multiply its magnitude, which is a 12, and then we get to sum up its argument here. That will be I 6 pi over 12. And then if you want to simplify that, there will be pi over 2 then. I hope I got it right. Yeah, okay, so it's pi over 2. That will be, you can consider that as our final answer, or if you like to represent that in its modulus argument form one more time, yep, this is how it look like. Okay, now you can leave it here, or here, or in its Cartesian form. For instance, in this case, cosine 90 is a 0, and then sine 90 is a 1. And then indirectly, we have a 12i there. Or you can leave it in the Cartesian form. Now, I hope that is clear. We're going to explore 2 more example under this example number 3. Right? Okay, next section. Let's look at what we have here. All right, now this is the next one. It looks very similar to the previous one, except there is a subtraction in both. So how are we going to deal with this? Okay. Now, as usual, we're going to rewrite this format so that there's only a plus first before we turn it into Euler form. So I'm going to write this as 2 cosine. I'll just copy that down one more time. Okay, that's the original one. Multiply by 3. Because there's a negative here, we will tend to convert this back into a positive form so that we can write its Euler form more accurately. Now, in this case, I can write it down as negative 2 pi over 5 plus I sine negative 2 pi over 5 here. Because we know that sine negative 2 pi over 5 is actually negative sine itself. So now you can see that it's in its correct form. Then we are ready to convert that to Euler format, which is this. Okay, and there you have it. And then the rest of the operation is very straightforward. So we have a 6, and then here we have negative pi over 5. Because it's addition, sorry, pi over 5. What have I done here? I've done a mistake here. Just let me clean this up. I think it's supposed to be, let me see here, 3, 6, negative 5. 3, and this is 3, 6, negative 5, correct. So it's actually a negative 5 pi over 15. That's my mistake there. And then now we can simplify that as I negative pi over 3. Okay, that's look more like it. And then there you have it. You can leave it in its Euler form, or if you prefer, you can turn it back into its modulus argument form again. That will be 6 cosine and then there you have it. If you don't have calculator like me, I do have calculator, but my calculator is not as powerful as what you are using, so it might be a bit tedious to use in this case. So I'll try to make use of what I knew about this trigonometry. Now that is the same as cosine pi over 3 minus I sine pi over 3 here. Now you can leave it in the Euler form in its modulus argument, or lastly you can convert it back to Cartesian form if you like. This is actually 60 degree. That is a 0.5. There's a 3. So this part here is 60 degrees sub 3. So it's 3 sub 3 I. Now that is your Cartesian form for this question here. So I hope that is clear. We're going to look at, I think there's two more subsections, right, before we move on to the next example. Subsection, okay, we are looking at the divisions right now instead of multiplications. Do check whether we are using addition here. Since all of them are in the correct form, then it's easier for us to convert that to into its Euler format. So we can write this as sub 2 ei pi over 12 divided by 2 e I 5 pi over 6. Yeah. And then next you can use your index rule more easily in this case. That will be sub 2 over 2. And then that will be I pi 12 minus 5 pi 6. And then that would yield this. So 10, 9. Okay, so it's negative 3 pi over 4 then. Just let me check briefly. Negative 9. Yeah, okay, so there you have it. You can leave it in this format, Euler form, or you could leave it in the modulus argument form, which is the same as this. Okay, and then just for you to see what you are looking at here, it's always best to draw its Argand diagram, yeah, before you make any trigonometry decision here. So we can see that that is a clockwise in the clockwise direction. That is actually 135 should fall within somewhere here. That argument is 3 pi over 4, negative 3 pi over 4. Okay, right, now there you have it. All right, now its magnitude, just to give you more info on this, its magnitude will be a 1 unit. Okay, so its magnitude is 1 unit here. You can figure that out from here. Okay, and then that's what we have. If you try to, you can actually leave it in this form if you prefer, in its modulus argument form, or we can convert it back to its Cartesian form here. Yeah, shouldn't be a problem. That will be the same as, because this is similar to 45 degree. It's just that for cosine it's a negative, so negative 1 over sub 2. For sine is also a negative. And then from here we have ourselves a negative half minus a half I there. So it's a half unit to the left, half unit down. And then if you obtain its magnitude, just let me try to see whether I got the correct magnitude here, because previously I thought that the magnitude is supposed to be 1. In this case, if I get the square of this, did I get it right? Yeah. Yep, correct. So if I square this, that is 1 over 2. So it's supposed to be sub 2. Just let me check. Oh yeah, my mistake here. The magnitude is not 1 unit. I think I mistakenly evaluated this. The magnitude is supposed to be, just let me correct that. So the magnitude is 1 over 2, because it's the same as square plus square. After you work this out, square root. So that will be 1 over 2, 1 over sub 2. So the magnitude itself is 1 over sub 2. Okay, So hopefully this is clear at this point. All right, now before we move on to the next section. Example number 4. Yeah. This look more like a past year paper questions instead of just a simple exercise like before. Now we are given a complex number z equal to 5 sub 3 minus 5i. Our first task is to figure out its magnitude for this complex number or its distance measured from the origin itself. Right? And then B, we're going to work out the argument in terms of pi. All right, now that is the first section. The second sections, we are given a different complex number in its modulus argument form instead. And then we are going to manipulate the division between these two complex numbers. So let's try to work out the first section. So we have a z equal to this. Now the magnitude itself should not be a problem. That is basically just Pythagoras theorem in this case. Okay, so in this case, if you work it out properly, we should get 2 by 10. Sorry, 2 by 5, which is a 10 unit, right? Now that is A. We are done. It's quite a simple task. And then secondly, we are going to work out its argument. Now, as usual, I will always advise you to sketch the complex number using the Argand diagram. Okay, now that would be like this is 1 point something, maybe around 6 or 7 units to the right, and then negative 5 units down. So that is further down somewhere here. And then its distance from the origin is 10 units. And then in terms of walking, we have to walk 5 units over here, and then another 5 units down, right, to get to the complex number z here. Now, how do we work out the argument? The argument in this case is measured from the real axis, clockwise measurement. This one will be our argument. So argument of z is basically equal to theta in this case. Now we know that because we measure it clockwise, it must be a negative. So I will just write down negative uptangent. So uptangent 5 over 5 root 3. And then that would give me a 1 over root 3, which is basically 30 degrees. Okay, and then there you have it. That's the argument. And then we are done. Before we move on, it's best to represent this complex number in its Euler form, for instance. That is actually 10 unit I negative pi over 6. Yeah, so that's our conclusions to the complex number. Now the second one, we are given a w in this form, so we can write the w in its Euler form also, which is ei pi over 4 instead. Okay, we are not doing anything here. For C, we are going to work out the divisions between these two complex number. Let's work out the division first. W divided by Z, so W is 2i pi over 4 divided by Z, which is 10 ei negative pi over 6 here. Okay, and then we know that this is 1 over 5 exponential, so we're going to add these two up. 3 to 5, 5 pi over 12. Did I get it right? Let me see. 3 here, 2 here, it's a 5, 12, yep, correct. So 5 pi over 12 here. And then that is basically our Euler form. And then to get the magnitude of this ratio is quite simple actually. It's just the magnitude of this. Which is the same as 1 over 5. because the magnitude of 5 pi 12 here is always equal to 1 here. Yeah, we know that this is always equal to 1. Okay. Anyway, for reference, we also know that EI theta, sorry, EI theta, I think I wrote it down wrongly. Hold on, just let me. Now, if you want to check whether this is correct, you can always try this out using this. Okay, so that is basically a magnitude of this is the magnitude of cosine 5 pi over 12 plus I sine 5 pi over 12. Magnitude of this. So magnitude of this is basically referring to the square of this add up with the square of this one here. And basically it's just a Pythagoras theorem that we are working on, which is actually 1 unit. Now that's the reason why this magnitude of this ratio must be 1 over 5 there. So I hope that is clear at this point. Okay. Now its argument is much more easier to obtain in this case based on the Euler form. So we know that the argument of this ratio is basically given by this term here, which is 5 pi over 12. And then this one actually fall within that domain of the argument lying between negative pi and pi. Okay, so 1890. Is it 90? Did I get it right? Let me see here. 1575. So it's 75 degree, right? So this is equivalent to 75 degree counterclockwise. So maybe at this point, just my personal notations, I will draw a diagram like this, just to remind myself it's a counterclockwise direction. Right? I hope that is clear for this example. We're going to move on to the next one.